So as now we move into Module 3, we're going to look at properties of graphs. So what kind of things can we notice on a graph? Do we report the y or the x value? Those kind of things are what we're going to be addressing. So more on functions and their graphs. Let's take a look. One thing functions can do, they can be increasing. And again, that's when they rise from the left to the right. So we're always reading in this direction because that's the way we do with English. So also, what we're talking about an increasing function, what's increasing? It's the y value that increases. The left, notice as we go from left to right, the x will always be increasing from left to right. So as x increases, what's happening to the y? Is it increasing or decreasing? That's really what we're talking about. We could also have a decreasing function. So this first one, let's draw a little picture. It's going to be going from left to right upwards. A decreasing function, since it's the y that decreases as the x increases, we get a falling graph from left to right. And then constants, well, that's just a horizontal left to right, no change, not going up, not going down. So a couple of rules to follow. Yeah, always use x intervals. So what we're going to report is reporting the x values that make the y value either increase or decrease. We'll look at an example here. So our answers will always be in terms of x, even though it is y that is increasing or decreasing or staying constant. Okay, we're going to use open intervals, and we'll see that the reason for that is because the endpoints are neither increasing or decreasing. Of course, we could talk about it all day, but it'll make a lot more sense when we see an example. So we're going to keep moving forward. And then always look at the graph from left to right, because again, in this situation, x is always increasing, going from left to right. Now, some of us are ambidextrous. We can both use our left and our right hand. We can think forward and backwards, and that is great. However, in looking at graphs, that can cause some potential problems. In fact, because we do at times look at the graph from right to left, we look at it backwards. And so if we're looking at it backwards, what was increasing is now decreasing, and so forth. So let's just look at an example here. We've got this graph. If we follow along with this, going from left to right, let's go with some green. We see that the y's are increasing from here. And then again, the reason we use open intervals is at this point, the sort of turning point where it goes from increasing and changes to decreasing. This point at the top is neither increasing nor decreasing. It's the top. It's the top of a mountain. Again, so we got decreasing, and then the same thing with this point here. It's the bottom of a valley, so it's neither increasing or decreasing. This little segment's increasing. This little segment's decreasing. This little segment's increasing. And again, when I say increasing or decreasing, we're talking about the y values are increasing or decreasing. The x, as we're reading this, the x is always increasing because we're moving from left to right. Okay. And as we talk about using x intervals to report our place, we would list this as increasing And where does it increase? Well, this first segment here is going this way. So it keeps going forever. And so like x, where does x start? I guess if you want negative infinity, where does x end? Positive infinity. Okay, so what we're going to do is it keeps increasing, right? This part here keeps increasing until we get to an x value of -4. So we're going to go from negative infinity until -4. We never really get to negative infinity, so we put a parentheses there and a parentheses on the -4. Because again, at -4, it's neither increasing or decreasing. And we union, okay, this part here, maybe we should change colors. We'll emphasize it. Let's go with it. So here's our increasing, right? We're increasing from left to right. We're increasing from left to right. We're increasing from left to right. And so then we start increasing again at -1, x equals -1, and we increase until x gets to +1. And again, parentheses on both sides, open intervals. That's what makes it, because the endpoints are not included. And then we have this last little segment going from +3 up to infinity. Well, I shouldn't say up to infinity because that's implying the y, over to infinity because that's implying the x coordinate, right? So let me, looks like I got a little negative x here in harm's way. So positive infinity there. Okay, so I'll put in my negative infinity is x way this way, right? Okay. And then we can list as decreasing. That's going to occur. Let's go ahead and highlight in contrasting color. See if this will work. Yeah, there we go. So there's a decreasing part. There's a decreasing part. Just two decreasing parts. And we can list that as starting at -4. So you'll see the endpoints here. You can kind of see it's going to be -4 to -1. Not always. I guess there could have gone constant in there, but on this particular one, that's a lot of times what's going to happen. So we go from -4 to -1. We're decreasing. You just kind of see the holes that were left by the increasing parts are all decreasing parts. Then we union. We're going to go from 1 to 3, which is from here to here. That's a decreasing part. So from +1 to 3, and then we're done decreasing. There's the rest of the graph is increasing. And then if we talk about constant, we could just list that as none. There's none, no part of the graph is constant. Okay, so that's one thing, is looking for increasing, decreasing, constant. And in calculus, as we move forward, that's where really what calculus is about, is rates of change. And so it's not about where we are, it's about where we're going. And so we're looking for where are the areas where our profits, for say, are increasing. We want to build our business. If our profits start decreasing, maybe we want to slow down or change something. And if things are remaining constant, then maybe we're okay. Maybe we want to make some changes. Okay. So that's the idea behind this. The other thing we want to realize is we were talking about those places, turning points, where the graph moves from increasing to decreasing or decreasing to increasing. So these things called turning points. Notice each of those places where it changes direction, it will form either a maximum or maxima, we say in Latin, or a minima or minimum, as we say in English. And we call those extreme points. Now, the type we're going to talk about are primarily relative, as we talk about relative maximum minimum. And what we're going to see is that there are two relative maximums, one here and one here. You're going to say, wait, one maximum is more maximum than the other. And that's all it means is, yes, they are both maximum for their area, for their neighborhood, in their region. So this one at -4 is the big kahuna for its area, and this one at 1 is the big kahuna for its area. Notice neither one is an absolute maximum, because this graph is going to go up till infinity, so there really is no absolute maximum, or we could say the absolute maximum is going to be positive infinity, because it just doesn't stop going up. So extreme points, we're going to list. Now watch how we do this. We actually do list both the x and the y values, but what we're going to say is we have a relative max at. That's a location at x equals -4. We could have just said at -4, and that would imply it was an x value at -4 with a value, or just valued at y equals 2. And I'll put the x and the y here. Now we could leave the x and y off, but if we do, it's not as clear, right? Maximum at -4 valued at 2 is how we could read that. So just get used to that. Whenever we're talking location, we're talking about the x. Whenever we're talking about a value, a function value, we're talking about a y value. right? This is a value. So values, those are y's, locations are x. And then again, we've got a relative max at x equals 1, and we could just say it's valued at y equals 0 in this case, because, you know, you could also, I suppose, list them as points, right? So this is negative 4, 2, and this one here is 1, 0. So 2 maximum points. For the minimum points, we do the same thing. They are relative minimums, and the first one coming from the left will occur here at negative 1, and then we just do it this way at negative 1 viewed at negative 2. Okay, so just kind of give you some mix up that the negative 1 is an x, the negative 2 is a y. And then there's also the relative minimum at positive 3, valued at negative 1. So x and y values. So notice we use that same graph again, and then where we were talking about increasing, decreasing, and those turning points are going to give us either a maximum or a minimum, depending upon certain things. And again, in calculus, we look at all of these types of things. Where are the maximum points? Because if we're at a maximum point, we know that the next thing that's going to happen is we're going to decrease. If we're at a minimum point, we know that we're changing from decreasing to increasing. And again, those are either good or bad things, depending upon what we're talking about. If we're talking about profits of our company, increasing is good, decreasing is bad. If we're talking about floodwaters, increasing is not so good, decreasing, the water's draining off, we're more happy. So we go along those lines. Okay, so let's look at graphing a piecewise function, because we want to be able to look at the graph to be able to tell increasing, decreasing, and all that kind of things. Now, if you look through the text, you know, doing this by hand is a bit of a challenge. We basically would graph the whole function. So there's two pieces here, right? There's a first piece and a second piece. If we're going to do this by hand, we would actually graph the full graph, and then for this first one, we would erase everything that was greater than negative 2. For the second part, we would erase everything that was less than negative 2, okay? Because each part is, we only want the part that's left. The nice thing is with Desmos, we're actually able to draw these. So let me see if I can click there. Let's go into Desmos, maximize it. It's looking pretty good. So what I'm able to do is put that first part, it's x squared plus 1. Right? So I can put in x squared plus 1, but I don't want it to be for everything. Let's see if I can remember the syntax. I think it's a comma and then a bracket. Let's see if I can get the brackets. I use my own, okay, there's a bracket. And then we want x to be less than negative 2. So I come back here and I say x less than, I think I can use this one, negative 2. Let's see if that works. And then it gives me the, I think I can, let's go back here, use the other bracket. I think I have to shift. Yeah, there we go. And let's see what it's drawn. I think the problem is that it's not this. Oh, actually, don't even need anything. Okay. So no comma. I think you can use a semicolon, but anyway, this is the half, and then from negative 2 we've got x squared. Now notice if I were to take that off, it would draw the rest of the parabola. What we notice though is it's not drawing. Let's see if I can set myself up here. I think I can actually draw on this. Is that we want to indicate that at negative 2, what's going on here? It's an open circle. I think there's a way, if we want to, in fact, let's go ahead and take a look at that. There's a way for us to go ahead and put that in there, we can say the point. We could list this point -2, 5, right? -2, 5. I think we can just plot that point. Let's see if it gives me the, I'm going to say -2, 5, parentheses, and then I don't want to label it, but there's a, when I plot it there, it gives me a dark circle. If I click here, I'm going to hold down on this part here. It takes it away. But anyway, there's a choice here. Sometimes the tablet works differently than the computer itself. There's a choice to make it an open circle. So we could do that, give that one a try. If I label it, okay, we'll keep moving. So then we want the second one, which is 2x minus 3. That'll be for x greater than. So let's just kind of keep going. Enter that. So I'm going to put in, what's it, 2x minus 3. We have that. And again, all we need here is our brackets. So we'll put in a bracket. This time we want x to be greater than or equal to -2. And then we see our line going. Just to make it nice, we'll finish our bracket. Just shifting that. Okay, so that seems to be working just fine. And then we could see that the point -2, -7, that's the one we want to leave as a solid dot because that's what's included anyway, right? So there's there's an option, but maybe if I minimize, I don't know. Anyway, it's not allowing. But if you hold on these little circular icon things here, it's supposed to allow you to choose, and you could choose that as an open circle for the top one. Anyway, we've got the graph here, we see it straight here, and that's, to me, this is the best way to go about drawing a piecewise function. Now you can do this on a TI-83. There's a syntax. It's a really complicated syntax. I've done it like once or twice, and then 5 minutes later I forget the syntax for it. But I guess if we were going to do this a lot, which we don't, I would go ahead and show you how to do that after it probably took me half hour to learn it again. But Desmos is very intuitive for the most part on drawing piecewise functions. And again, what I really like about Desmos is it's got a lot of user interactivity. And we're going to allow you to use Desmos through the testing process because we have the lockdown browser. So you can go out to this, just use Desmos. It's got a lot of tools. We're going to introduce these tools to you as ways of learning and ways of doing so you become familiar with it. Also, I want to respect our active duty military. Oftentimes they have difficulties while they're on deferment in getting certain technologies and such, but oftentimes they will have access to Desmos. So we're going to make that available to y'all. Okay, so that's how I would go about graphing using Desmos, and you can look up piecewise functions with Desmos. That's what I did. Nice little video. That's how I learned it. Or you can watch this again. Okay, so let's go to the next one. So the summary. There are two main types of symmetry. I'm sorry, I look at symmetry and I see summary. Symmetry. So symmetry is each side is similar in some way, and there's two that we're going to consider. We're going to look at y-axis symmetry, which is the y-axis itself, right? Here's our y-axis. Actually cuts it in half. So this is kind of artistic symmetry where we're probably fairly familiar that the left side and the right side look the same. So here's our, if I get my hands right, here's our left side, Here's our right side, and it's the y-axis that cuts it in half, and they're similar, right? You flip one onto the other and you'd have the same thing. So that's one type of symmetry. We're going to see that this is also caused by what we call even functions. And if you're thinking the square has something to do with the even, you are exactly right. We'll look at those even exponents create even functions. The other type of symmetry we get is something called origin symmetry, which is symmetry about a point. I like to call this spinner symmetry because to me it reminds me of like one of those spinners you had in a game where if you were to spin this side 180 degrees, you would land right on the bottom, and this going 180 degrees would land right there. So if you spin it, spinner symmetry, so 180 degrees. Spin it around itself. And as you can see, the exponent is an odd exponent in this case. 3 is odd. So we're going to see this is tied to being an odd function. Not odd because it's strange, but odd because it's not even. I guess that's how they define odd. It's even and odd, right? 2, 4, 6, 8, those are even numbers. All the odd numbers. In mathematics, we see those play some interesting roles. If something's even, it's got a certain look to it. If something's odd, it's got another look to it. And artistic differences as well. Okay. So let's take a look at this more deeply. Even and odd functions, we've kind of defined them, but let's see some properties that come up. So an even function, again, will have an even exponent, and it will have symmetry about the y-axis. So the y-axis cuts the graph in half, and it's doing that. One of the features we see is that when x is negative and positive, the output value is always the same. So it doesn't matter whether we say f of negative 1, we get 1. F of positive 1, we also get 1. So what we see is with even functions that the input of the negative value of x is going to be equal to the positive value of that same x value, right? The absolute value, let's call it that, will have the same y values. So we're going to see that. We'll define that clearly in a moment. So that's a property of even functions. We can use it to find it, but I'm also going to focus on that exponent there. Odd functions, and again we see this with the exponent being 3, that's partly what makes it odd. It's got this spinner symmetry or origin symmetry because the origin has to be where it is, right? If we moved it off the origin, it would no longer have that kind of symmetry. It would look exactly the same. We could move this up and draw it up higher, but it would no longer have origin symmetry. But what we do know, hopefully we can spot, is because we sort of get this thing happening that what creates a symmetry is that a particular x value, when you have the negative x value, its y output value is the opposite of the output for the other function. So we notice that f of 1 equals positive 1, f of negative 1, oops, I guess it should be this way, equals what? Negative 1. So what we see is that, well, we're going to define this. It's a little harder to see, but basically, if we do know the value for a positive x value, we know its output. We know that if we take the negative of that, the other side, it's going to be the opposite. So let's just kind of look at that up here. So this even function thing is a little bit easier to understand. This one is kind of confusing, but it just tells us whenever, if you take the opposite of x, you get the opposite of y, right? So take the opposite of x, which negative 1, you get the opposite of y as well. Okay, so that says, think of those negative signs as being opposites. Okay, so those are one way, and the book will really focus on that. But I'm going to show you that if this is not real clear, which it takes a little while for it to become clearer, but I still will focus on the exponents, and we'll still be able to identify whether a function is even or odd, which is basically what we're going to be having you do. So here's some examples. Is this function even or odd? Or could be neither. So I did talk about that we'll only get even function if all the exponents are even. So again, we could look at this in 3 different ways, actually. We could look at its graph. So if we would go and graph it, and I'll ask you to go ahead and do that, but I'll just do a quick sketch of it. It would be a parabola multiplied by 5, and plus 3 will raise it up. So it's going to be something that looks like this, where the bottom's at 3. It still has y-axis symmetry, so yes, it is even. Because if we didn't add that 3, we would be down here. RC moves it up. What it gets us thinking is, what would be the exponent on the 3, or the variable on the 3? Well, I don't see any variable there. One thing you have to remember is that whenever you take any number and you raise it to the 0 power, you get 1. So 3 times 1 is 3. So another way of writing 1 would be, with a variable, is x to the 0 power. X to the 0 power actually is equal to 1. In every case except if x were 0. 0 to the 0 is the one case we don't talk about because it has problems. But let's not let one little problem spoil us, okay? So we can think of this as x to the 0 power. It's now all the exponents are even, okay? So we're good with that. We're happy with that. This is even. Let's take a look at the next example. And what we see is, we're asked if this is even, odd, or neither. Well, we see an odd exponent here. Oh, this is an invisible exponent. Hopefully you remember that the invisible exponent on the x is x to the first power. 1 is a odd, so far we've got 2 odds. But what's going to happen with this 2? Well, from our last discussion, that's 2x to the 0 power. That's an even. So we got odd, odd, even. This I'm going to propose has neither type of symmetry. It is neither even nor odd. And you could also use the definition. If you look in the notes, it is done that way. If you look in the explanations, they will use, let's see, let me go back. They will use this little box up here. Okay, let me do this. So let's see what's going to be the easiest way for me to, if I back up enough, I get to my Desmos calculator again. What I want to do is graph this. And so I think I can do that by just kind of getting out of here. Let's go to Desmos. 5x to the 5th minus 6x plus 2. So do a clear one. X, and I'll do a to the b. So I use that one to put the 5th if I'm not doing the other one. I arrow over to kind of get down on the line. And then what did we have? We have minus 6x, minus 6x, and I think it was plus 2. Let's make sure, yeah. And we see that, yes, indeed, our center point here is not on the origins. It still sort of looks like it would spin. It would have maybe y equals 2 symmetry, but we don't talk about it. It does not have origin symmetry. Okay, so because of moving it up. And what did that was that 2 right there. So we've reached the end of Module 3, the direct instruction part anyway. What's left for you to do, the tasks you want to complete, the learning activities in Module 3, working through the assigned problems. As you have any difficulties in understanding, remember our resources of online tutoring, instructor office hours, as well as working with peers through the discussion forums that are available in the learning management system. So hope all is well, keep making good progress, and take care.